Having me, it's an honor and a pleasure to be here speaking to the ACM Student Conference, and awesome lineup of speakers that I'm also honored to be included with, and the company of people like John Hall and Doug Hofstadter. You've got a great lineup, and I hope that you're going to enjoy this starting kickoff presentation. I've called it "It's Getting Cloudy" because I do live in Seattle, and yeah, how many people have been to Seattle? So you know, it's actually when visitors come to Seattle, it's always sunny for some reason, but I think that's just the trick we play on people. But it's cloudy in Seattle weather-wise. It's also incredibly cloudy as far as computer technology in the industry there. If you look at who are the big players in the cloud today, it's Microsoft. I'd like to consider us a big player. Microsoft, Amazon, Google, VMware, and in fact, all of us, all our cloud centers are in Seattle. So Amazon's based in Seattle. VMware's cloud group is now based in Seattle. They've got a cloud laboratory. They just started there. And Google's obviously got a big presence in Seattle. So it's a lot of cloudy stuff going on in Seattle besides the weather. I'd stop here for just a second to talk about my background and how I got into Windows Azure and cloud computing, because I've only been in cloud computing for the last year and a half. Prior to that, I went to a school that is almost as good as University of Illinois. It's Carnegie Mellon University. I got my PhD there in computer engineering back in 1994. Went off, worked at a few small companies, then IBM Research, then started a company of my own that I sold to Microsoft in 2006. I've specialized in Windows internals. You'll see there a couple covers of Windows internals books that document the internal workings of the Windows operating system, and then I've written a bunch of tools. Has anybody been to sysinternals.com and used tools from there? So good, some sysinternals fans in here. Worked on those. I continue to work on those. And finally, I'm also a new first-time novelist. This is a book that I wrote early and published earlier this year called Zero Day. I'll be giving away this copy at the end of the presentation. Come up with some sneaky question to ask you, and the first person to answer gets a signed copy of the book. So let's get right into it. Let's talk about the shift that I see, and the reason that I went from Windows over to the Windows Azure group about a year ago was really looking at the changing landscape in computing and realizing that lots of big things are happening right now. And if you look at the computing history as a guide for shifts in computation, you start out with the original era, or epoch, which was the thin client mainframe era. It's actually, for most of you in this room about your age, when I was the same age, we were coming off the transition of this epoch. So at Carnegie Mellon, for example, when I took some classes there as a high school student over the summer, we were programming against mainframes, TOPS 20 digital computers with thin clients, and we'd log into the systems with VT100 terminals. But what happened right as I joined Carnegie Mellon is we started this massive transition to client server computing, and that's when the PC era really kicked off, and you started to see the waning of mainframes. Still obviously heavily in use, but less relevant. The world just wasn't focusing on mainframes. Mainframes were to run your legacy IT infrastructure, but all the new cool happening stuff was happening on PCs. And what we're seeing right now is the beginning of another epoch, I think, which is, we're at the beginning of it, which is the mobile cloud epoch. And this one is, now, mobility has just exploded in the last 4 years. I think the iPhone had a big role in that explosion. As everybody's carrying around computers in their pockets, and now we've got tablet devices, a new category. Everything's mobile, and that's where all the cool hip stuff is. But for those mobile devices to be useful, they've got to talk to each other, and they've got to store data someplace. And they're not doing it on the devices themselves. They're doing it up in the internet, up in the ether, up in the cloud. And so it's impossible to talk about these two shifts separately from each other. They're happening together, although there's an aspect to cloud computing that is independent of mobile, and that's simply outsourcing your infrastructure to somebody else so that they can run it. So there is an aspect to cloud computing that's independent of mobile, but certainly you can't talk about mobile without talking about cloud computing backends and all of the services that are provided to the mobile devices, including applications that are all storing their data and basically front ends to cloud services. And if you look at the patterns of workloads that people are running on computers these days, there's a number of different trends that we see when we look at the customers that are Microsoft customers and the kinds of workloads they run. with very different patterns in terms of their workloads. And one of them right here is a company called Riskmetrics. What they do is data analytics, and they do batch processing of huge amounts of data, running their analytics over that data. The way that their workload operates is that they come up with the computation that they want to perform, the analysis they want to perform, then they launch this massive job which literally spins up thousands of computers all crunching the numbers, finishing the computation, and then they're all shut down. So it's a very bursty type of workload. If you look at another example that we've got, this is an internal property. It's called docs.com. It's Microsoft Office integration with Facebook that kicked off about 2 years ago. And when that launched, of course, there was hardly any users. This is kind of an example on a small scale of the everybody's internet startup dream. Starts out very small, get a few users, and then buzz starts to grow around it, and you see this spike in usage that is really hard to predict, hard to gauge, hard to keep on top of. And yet, if you're not satisfying it, you're making your customers unhappy and losing customers. Another one is the unpredictable bursting scenario. And eBay talks to us a lot about this one that they see when it comes to auctions and the usage of eBay. They have a very hard time predicting the usage patterns that they're going to see on their servers because they just don't know when there's going to be hot items that appear on eBay that cause this flurry of activity seemingly for no apparent reason. Just people being interested or just random coincidences of people doing and purchasing things or bidding on things on eBay. So they've got a very spiky type of behavior, very hard to predict. And then finally we've got Walmart, which has a very predictable pattern to their workload. It's obviously it's very seasonally affected. Walmart being a big consumer retailing operation, they see around the holiday times, for example, everybody's going off and getting ready and buying presents for their friends, and then after the holidays too, everybody's going back into doing exchanges. So they can predict those pretty well. When we look at our own properties, we also see massive fluctuations in data. If you look at Bing, and I'm sure everybody in here Bings instead of Googles, or you Google on Bing rather, right? Because it is okay to say that because Google is the verb. So it's okay to say I Google on Bing. All right. I Googled it on Bing. Hopefully one day you'll be saying I Binged it on Bing, but we'll start with small and hope that you just do something on Bing. So in any case, when we look at Bing's workload, if you look at different parts of the world where we've got Bing users, you can see that over in Japan, completely out of cycle with the kind of workload, the kind of query activity that we see coming out of the UK, which is in a different time zone. The time of day, the business hours don't overlap with each other there, and so you get this inverse, this kind of synergistic sine wave from those. And then we've got other patterns that we see from other industries. This is, again, a very predictable pattern around shopping times for these companies. Walmart, Target.com, Toys R Us, Barnes & Noble, all consumer retailing outfits. Again, big spikes right before the holidays. And then you've got this other category of companies that have also predictable spikes around certain times of the year, specifically tax time. It's kind of interesting because you would expect tax time, you'd probably think intuitively there's going to be one spike, which is right around tax time, but you can see 3 spikes here. And I'm just guessing, I haven't gone back to look at the source of this data to see exactly what these spikes are from. I'm guessing if you look at right after January, that's everybody's getting their end of year statements and they've got all their data ready to file their tax returns. So these are the people that are on top of it, that go to file their tax returns early, get it out of the way. And then you can see that second spike there, that's probably April 15th. And then you can see this other spike over there. I'm guessing that's over in October, which is the late filing deadline. So that's how I view that, and also the beginning of the year. So what is a cloud? And so far I really haven't defined a cloud, and I've talked about how cloud and mobile fit together. I've talked about how these different workload patterns, but what is a cloud? My definition for cloud, and there's no universal accepted, this is the definition for cloud. So I've come up with one of my own based on what I see people using the term cloud for, and really the characteristics that I think define what the intent of cloud computing is, and that is on-demand, scalable, multi-tenant, self-service compute and storage resources. So that's a big, long phrase. Let's break that down a little bit. On-demand. When you talk about on-demand, the contrast to on-demand is you have to go and request some resource and through some process, and at some later point in time, not very under your control, you'll get access to that resource. On demand means I need more resource, and you get it right when you need it. If you look at the server provisioning, for example, server provisioning is a process whereby if you need resource, you've got to go and buy new servers, bring them into your data center, wire them up, connect them to the network, install the operating system on them, install the software on them, configure it according to whatever corporate policies that your data center needs. It's not really on demand. It's some point in the near future. If you look at Scalable, again, looking at a traditional kind of data center in a company, it's not very scalable. The applications, the slides are moving on their own, sorry about that. See if I can go backwards. The data centers aren't really scalable. The applications aren't really scalable for your traditional server type of applications. If you look at most server applications, they're designed with no scalability in mind or scale up in mind. I'll talk more about that later. Whereas when you talk about cloud and the ability to handle these workloads, you need to be able to scale out to big numbers of resources in many cases. Multitenancy. The benefits economically of the cloud computing model are totally based on multi-tenancy. If you buy your servers yourself, and these are my servers, and I run my stuff on it, most of the time what we see is that you've under-provisioned the servers because you have to be prepared for those bursts in the workloads that we saw on the previous slide. If I want to be able to handle shopping season, well, I need X number of servers. But the rest of the year, those servers are all sitting there doing nothing. If I have a shared pool, though, of resources where we all share the servers together, then you saw that Bing workload where it was synergistic there. Well, we can actually share the exact same pool of servers and have both of our workloads satisfied because it always adds up to this capacity that we're sharing with each other. So multi-tenancy is a key part of the cloud economics, is I'm not paying for stuff that I'm not using. Other people will make use of it. And then finally, the self-service aspect of it, which kind of goes with the elasticity, the scaling part of it, the on-demand part of it. Again, if you need a server, if Walmart wanted to have a new server in their data center, they wanted to deploy a new application to their data center, a new IT app, for example, or you wanted to do a startup and you bought your own servers. Well, sorry about that. If you, the self-service part of it is that for the enterprises especially, is that the person that wants to deploy this application to the data center has to submit forms to the IT people that specify exactly what they need, what server they need, what operating system they need, what software they need on it, how they need it to be connected to the network. They can't do it themselves. The IT staff then takes that order and then goes and does their thing. Whereas self-service means that I can go and just do it myself. I can say, I need these number of servers, and I need them connected in this way, and they need to connect to the internet, and here's the domain name that I want for it, all on my own. I just go to a portal, and I do it on my own. I use tools to do it on my own. Don't have to go through anybody else. So these two graphs here, which have been animating on their own for some reason, show the contrast between the traditional world of my own data center, my own servers, versus a cloud, which is shared by a bunch of people. In the data center case, you can see the line here is one that's the kind of unvariable workload that's growing over time. But once I realize that I don't have enough capacity to service the new workload, I go buy those servers. It takes a while to bring them in and configure them. And once I've got them configured, of course, the load is dropped, and now those servers are sitting there doing idle. Cloud provisioning, if I can simply, on demand, elastically, scale my resource usage up and down, then I can keep track of the workload and match the resources to the workload's demands. And this, in a nutshell, I think this slide really captures the value of cloud computing as a general concept and makes a strong contrast with what we've seen with client-server computing and my own servers, my own resources, my own data center versus a shared pool that I work from. To be clear, there's two kinds of clouds in this model. There's the private cloud and there's the public cloud. So just because I say it's multi-tenant or shared doesn't mean that I'm sharing it with the world. That's what we call the public cloud, and that's what Windows Azure is. It's anybody can come and use our computing resources. The concept of a private cloud is also really important. It's I don't trust data in somebody else's data center. It needs to be in my own data center. Or I've got special needs for my computing and my data. I need it certain certifications. I need certain kinds of hardware to run my workload, and so I'll create a private cloud that I share among other people within my same company that I trust, and it's not this open to the internet stuff that I'm working with Windows Azure or other cloud providers. Further breaking down from another dimension, different types of clouds, there's infrastructure as a service. How many people have heard of infrastructure as a service, or IaaS? So a bunch of you have. This is actually the canonical type of cloud. This is the first type of cloud that really hit consciousness, and Amazon's the one that really made this sink in for people when they launched EC2. All right, I have to control this mouse. EC2, infrastructure as a service, what that means is you're renting somebody else's servers. They're providing the infrastructure. This is what the as a service means, part of the cloud. When I go rent Amazon's EC2 servers, I can deploy virtual machines to those servers, and I'm in control of everything in those virtual machines. Those virtual machines are very similar to the kinds of virtual machines I could deploy on my own desktop, on my own servers. I control what software runs in them. I can put any operating system I want to in there, including Linux. I can put Windows in there. I can put anything that their hypervisor will support. So an example of this is, of course, Amazon EC2. VMware's vCloud is another example of this kind of infrastructure as a service, clouds that support deployments of virtual machines with arbitrary operating system images into them. The next type of cloud is platform as a service, PaaS we call it, and this is the one that Microsoft's making a big bet in. This is a little bit different view of giving out or making the resources available. Instead of giving you raw virtual machines, what we do is give you a computing platform where you give us the application and then we deploy it to the computing platform. Now, in Windows Azure, the computing platform happens to be built with virtual machines, but the difference between our virtual machines and, for example, Amazon's virtual machines is that we've got a computing platform built on top of those virtual machines that your application interacts with, and you get some benefits out of that interaction. Instead of you having to bring us the operating system, install the application into it, when you've got an update to the application, deploy the application into it, what you do is you bring us the app. You bring us a description of what the app needs in terms of resources, like how many virtual machines it needs, how they need to be connected together, the configuration that you want us to give to your app, and then what we do is we take that your app code, we launch virtual machines, and then we deploy your app code into it. And then we give your app code the config that you wanted. If you want to update config, you give us the new config, and then we'll go and update your app with the new config across however many virtual machines your app has said you wanted. Not just one, but any. You could have 1,000. You could have 1,000 virtual machines that you're running this app in, and you say, here's new config for this app. We'll go and put it on all 1,000 machines for you. You don't have to worry about it. Really, one button, and you've just deployed it. And there's other examples of this. This is the hot area. Infrastructure as a service is already being recognized by the industry as commodity, and platform as a service is where the action at it is for building a cloud platform. And so you see even Amazon take steps towards platform as a service. They've got something called Elastic Beanstalk, which is really you come and bring your Java Apache Tomcat website, and they'll deploy it onto virtual machines with that stack inside of it. Other examples, Google App Engine. So these really are the three players, I think, right now. App Engine, us, and Amazon in the PaaS space, in the public cloud space. Google App Engine is even a more restrictive model. Instead of getting a virtual machine, you bring your app, and you're probably running in the same virtual machine with other customers running their apps. Because you're sharing a virtual machine provides a nice security boundary, but you're inside the same one with other people, so the application model is very restrictive there. It's Java or Python, Java or PHP, and you can't access the local file system, for example, where by contrast with the virtual machine, you can do whatever you want to inside of it because it's really your security resource from a security perspective. And then finally, we have software as a service. Software as a service is the other cloud term that you'll hear, so it's IaaS, PaaS, and SaaS as we call it. And SaaS is really what IaaS and PaaS are all about. Software as a service is really, you're building services on top of these clouds. When somebody comes and deploys an application to Windows Azure, they're doing it because they want to give some service to somebody else, whether that's through their mobile devices, talking to the application, or a website. It's software as a service. It's the finished product. It's a cloud app. And examples of this have been around for the kind of interesting thing to me is that people talk about clouds like there's some new thing. Clouds, wow, look at this, cloud computing. When it comes to at least something running up on the internet and running at massive scale. But we've seen software as a service for a long time. Hotmail is an example of software as a service. Messenger is an example of software as a service. It's these apps that run in somebody else's data center that you're just taking advantage of. When you go across the spectrum, so I've talked about servers in your own data center, infrastructure as a server, platforms as a service, software as a service, you're going right on this chart here. As you go right, you have to manage less and less. And this goes to that part of the economics. With the Windows Azure Platform-as-a-Service, you don't have to patch the operating system. We do it for you. If you do infrastructure as a service, you've got to patch the operating system. And so as you move to the right, you manage less and less. The downside to that, if you want to view it as a downside, is that you lose control. So Google App Engine being a more extreme version of Platform as a Service, you've got very little control over the environment that you run in. You're running in their high-density hosting environment. So the trade-off there is less control, better efficiency, less overhead and management. And the economics of it all, when you combine it with the elasticity, the self-service, the on-demand, the economics of sharing the platform, is what's pushing everything in this direction. Let me give you this little diagram shows you a contrast between infrastructure as a service and platform as a service. So for infrastructure as a service, what you do is, as a developer, software developer, you got your VM images that you pull out of your library, some images that represent the application. You configure VMs that have your database in them with your operating system in it. Then you pick and create your front-end servers, the ones that are, for example, having the website front end. So you're picking images that have the web server installed in it, or you're installing it into the base operating system image, you're configuring it. You're provisioning your database at that point. Then you're installing the real application on top of the web server. You're configuring the load balancer so that it sprays requests across your front end. And finally, you're managing the VMs on an ongoing basis, the database, patching it, and so on. Now, here's platform as a service. These faded boxes are what the platform gives you. So the platform gives you a cloud database service. You don't have to worry about the database. It's there for you just as an API that you call. We also give you the virtual machines. This happens to be the Windows Azure version of PaaS. So at that point, you don't have to create the database. You don't have to provision the systems it's running on. They're there. So you deploy your database to it. You deploy your application. And that's it. In fact, the load balancer is configured because you've told us how you want it configured. So you don't even have to do that. And you're off and running. So a lot less to manage and worry about. So that's really kind of an introduction to the cloud and what the cloud is and the different types of cloud. And like I said, Windows Azure is focused on platform as a service. What I want to talk about now is switch to looking at what it means to build for the cloud. And the cloud meaning services. Services that if you're doing a software company and you've got a mobile app, what it means to build an app that can scale with the number of users that you've got, to be available anytime that they want to access the app. Nothing worse than having a customer go to your website or pull up your app and have it hit an error because your service is down. It's down for maintenance, or it's down because the hardware it's on failed. So how do you deal with cloud scales? And a lot of people don't have to deal with scales like I'm showing up here on this slide, but you might actually, most people strive to. This is the kind of scales that Facebooks and Twitters have to deal with. It's also the kind of scale that, as a cloud platform provider, we have to deal with. So the lessons here, while they help you scale to these numbers, are also useful for even scaling to smaller numbers if you're starting out small. Millions of users, tens of thousands of servers, thousands of applications. That's the kind of scale that we run in Windows Azure. Give you an idea of the amount of storage resources that are built on our cloud platform, storage capacity for people to store data, which we're building out according to the demand on that data. Today, we've got about 70 petabytes of storage available in Windows Azure, and given current growth trends of people adopting the platform and storing data in Windows Azure, we expect to have that built out to 200 petabytes of data by the end of next year. So gigantic scales, and literally, like I said, tens of thousands of servers. We actually expect to double the number of servers we've got in production by the end of next year as well. So how do you build for the cloud scale? Oops. How do you build for cloud scale? How do you build for cloud availability? These are the two things that I'm going to talk about now. Starting with how do you build for cloud scale. So I mentioned that there's two ways to scale an application. There's the ScaleUp model, which is, this must be an incompatible version of Office on here. This is not scaling the way I expected it to scale. The ScaleUp should be scaling the RAM as well as the disks. This is the traditional server model of scaling. So if you take a look at server applications, a lot of them aren't designed to scale at all. They're small, single function type of apps, and the developer writes them, they do their job, and they live their long life. There's a class of server applications that do need to scale. A database application, Oracle DB or SQL Server, these are applications that need to scale. They're traditional server applications, and the way you scale them is by scaling them up, meaning that they have a bigger demand on capacity, that you throw more resources at the problem, and the resources you throw are more RAM, more disk, more memory, more CPU. And that's scaling up. And we're seeing that's kind of the mainframe model. Whoops. The mainframe model of scaling, which is to create massive, bigger and bigger machines. And Windows has been following this scale-up pattern for a long time, where now it's going to be, as of Windows Server 2008 R2, it scales to 256 CPUs, and it's scaling bigger. Linux scales to massive sizes, even bigger than that. And Windows 8 is going to scale even bigger than that. But the other model is the ScaleOut model. So you start with one system, you scale it out by adding more instead of scaling up. Now, which do you pick in the cloud? The number one lesson, I think, of the cloud and actually managing any kind of system is that heterogeneity is the enemy of scale. And what do I mean by that? Well, if you've got a complex system made up of lots of different versions of the same thing, that means you've got, if let's say n different versions, you've got n different ways of managing that system now. You've got n different types of failure modes to deal with. You've got n ways of configuring things to deal with. You've got n ways of testing things to deal with. And so as you get more and more mix of resources, more and more complex heterogeneity in your system, you just get bogged down with having to deal with all these details. Versus you just having, for example, in the simplest case, just one of everything. Now, I update it, I test one. I understand how that one thing fails, how it performs, and I can manage my system a lot more efficiently. So the lessons that we learned in Windows Azure from looking at Bing, for example, which scales also to tens of thousands of machines, and also our internal IT operations, which run essentially private clouds internally for Microsoft, for internal Microsoft sites and Microsoft properties that I've hanging off Microsoft.com, is that these guys have like 50 different types of servers in their data centers, these other Microsoft IT operations people. Because somebody calls up and says, hey, I've got a new cloud property and it needs to have X numbers of disks of this size with this amount of RAM because that's what the application needs. That's how it scales. And so they go buy another version of a server and stick it into their data centers, yet another thing for them to understand and manage. And the complexity just blows out the roof. And what the complexity causes for them running the infrastructure is what's called a higher cost of goods and services, or COGS we call it, which is for every hour of compute, it costs N cents to run that server based on all the management overhead that we got to deal with, all the problems we got to deal with. And the goal for efficient cloud computing, both for obviously internally and to sell services to customers, is to get that COGS down so that we can lower our costs, lower customer costs, and just operate more efficiently. So the lessons we've learned here are define scaling boundaries and then scale out instead of scaling down. And I'll talk just a little bit about how we do that. Here's an example of a canonical 3-tier application. This is a web server that's got some business logic in the middle tier and a backend, which is durable or persistent storage. Lots of websites and cloud services are built with this kind of basic structure. The front end is what talks to the world. It's sitting behind a load balancer because you've scaled out the front end. And the front end is stateless, meaning it doesn't store anything that needs to persist on the local machine. It's really just a broker for client requests coming into the system. Then it hands off client requests to the back, and the load balancer is basically spraying requests across them as part of the scale out to get all of them utilized. Then what they do is hand off the request to the middle tier that's actually going to go crunch the request. The middle tier is also stateless. It's processing, it's video encoding, it's doing some computation on the thing. What it does is when it comes up with an answer that it needs to save for the user, it stores it in some persistent durable storage, which a lot of times is a database, it's a file system. In the cloud, the database or file system is provided for you. Those services are provided for you, so you don't need to worry about it. If you're building this on your own servers, you actually typically install the website, and then you create a virtual machine that has the business logic in it. You might even put the database in that same tier or in a different virtual machine, but you're creating the database, and then you're worrying about how to scale that out. What we do is we've scaled out the database. We've created a middleware service, which is persistent, durable storage. When you write to that database, it's there. We guarantee that it's saved. It's stored across actually 3 different disks, and it's geo-replicated at the same time to another data center in case that one fails. So you don't have to worry about that. You just do the kind of the easier stuff, which is writing stateless scale-out services. And the Windows Azure application model, what we try to do is make it easy for you, and I apologize for the formatting, this is just a different version of Office, maybe with the wrong fonts not installed. But what the service model, which is what we call the application model in Windows Azure, what we do is make it easy for you to write a scale-out application. So what we'll do is let you define what your application looks like to us. You'll say it consists of these 2 tiers. You don't need to do the 3rd tier because you're going to use persistent storage. And you say, here's the code that runs in the front ends, here's the code that runs in the back ends. Here's the configuration for the front end, here's the configuration for the middle tier. And they need to run in VMs of this size. That's my scaling unit. VM on the front ends, I want to scale out by 2 cores at a time. So you'll say it's a small virtual machine. And now when you scale that thing out, you'll get virtual machines created with 2 cores in them, a certain amount of memory, and so on. Those are called roles. So your front end is a role, your middle tier is a role. Here we've got 2 instances of the front end, 3 instances of the middle tier. All you had to do to create those is tell us you wanted 2 of one and 3 of the other. And you told us the size of the virtual machines. The platform goes and creates those virtual machines, installs your code into them. So the virtual machine in this case, in this example, is the scale unit that we've got. And this is the scale unit and the kind of model that we provide for customers to take advantage of on our cloud platform. It's also what we use internally. So all of our infrastructure itself that builds this platform is modeled in the exact same way. So this is a case of where we do the scale out, scale by virtual machine sizes as well, and that's why we pass this on to customers, because we know that it works for us. So that's the basics of scaling. Now high availability, that's a much harder problem to deal with. Keeping these services available. And what do I mean by keeping services available? Again, how many people in the last month have gone to a website and seen it down for maintenance? So a few people have. And what's your feeling when you run into that? It's like, this is ridiculous. It's a joke. Come on, get your act together. I'm going to go to this other website where I can go do what I want to do. If you can, you'll go to the option. So when it comes to cloud applications, we have promises to customers that we make about how available our cloud services are. We also want to help people that build on our platform create promises that they can provide to their customers. Your customers, if you're creating applications on the platform, that provide high availability. If you look at the high availability, people measure availability in number of nines. Say, how many nines are you available? And they'll say, I'm 4 nines availability. What does that mean? It means that I'm down at most 1 hour a year. I'm unavailable. Now think about what it would mean to write a piece of software that's down no more than 1 hour a year. And it's a piece of software that you want to update too. Like, how do you update that software and keep it available that amount of time? And it's running on fragile hardware. So the thing is, it's very hard to achieve these kinds of numbers of availability. If you look at what we're providing, this is kind of industry standard now for public cloud platforms and what kind of SLA we've got with customers, service level agreement. For us, it's 99.95%. For if you deploy an application to us and you do your part of the contract, we'll do our part and make sure that customers can reach your service 99.95% of the time, which if you look is, well, it's not on there, but it's somewhere in between 8 hours and 52 minutes of downtime a year, or outage a year. So it's very small, and that's a statistical number. It's not like we're guaranteeing that's how long you're going to be down. It's what we believe we can statistically guarantee. If we fail on our side of the contract, we of course reimburse you, and of course we don't want to fail because we know that missing our SLA with you, it's not going to be a good experience with you. So we've got incentives to do better than that. How do you maintain high availability? Well, you design a system that just knows it's going to fail. It just is inevitable that it's going to fail. One of the things that I'm sure you've learned as you've written software is that you're going to write bugs. It's just inevitable. You're going to make mistakes. Anybody in here not ever make a bug in their code? Because we've got awesome jobs at Microsoft for you. You do. So actually, I've never had a bug in any of my software, so I'm an exception. But software of any complexity is going to fail. Even no matter how rigorous your engineering processes are, no matter how good your testing is, the systems are so damn complex that they're just going to fail. You just have to assume they're going to fail. Second, hardware failures. Hardware fails. Now, most people, you really don't think about hardware failures. You buy a system, and very few people experience hardware failures as they're using their computing devices. It's almost always software failures. When you start to deal with the kinds of scale that we deal with hardware, we're buying tens of thousands of machines. You see every single different weird, bizarre failure case that these things can have. Everything from the firmware getting corrupted and the system not booting, to the disk failing, to RAM just disappearing on you as the system's running. Just poof, it's gone. You had RAM, now it's not there. Every single thing that can fail in a server, we've seen it fail. And sometimes it does take us by surprise too, when we see some of these new failure modes that we just like, wow, if a server can fail like that, nobody had any idea that a server could fail like that. And so it's always kind of interesting to watch these kinds of failures. So how do you deal with these kinds of failures? You've got to have two things in place. Really, you've got to detect the failures fast, you've got to recover from the failures fast, and you've got to have redundancy wherever you can. So think about that 1 hour case, which is like let's strive for that 1 hour availability. If there's a server failure, how long do we have to detect that it failed? Well, if we take an hour to detect that it failed, we've just blown our SLA. So we've got to detect it fast. And then, let's say we detect it in 10 minutes. Well, how much time do we have left to recover before we blow the SLA? We've got 50 minutes. So we've got to recover fast, and that's just hoping that there's only one of these a year. Plus, so one of the ways that you can mask failures is with redundancy. So wherever you can, put in the redundancy. That's the other part of it. So let's take a look at how we put in redundancy into our data centers. This is a high-level data center architecture diagram for what Microsoft data centers look like. In fact, most data center architectures you look at from any company, they'll look a lot like this picture. At the top, we've got these monstrous routers that go out to the internet. They're huge. They've got fat 10 gigabit pipes, lots of ports, pumping things out to the internet. This is what our large-scale services like Hotmail and MSN.com and Microsoft.com talk out to the world to. And we need gigantic data center routers to get good responsiveness for everybody that comes to those sites. Then we've got this other tier, aggregation routers and load balancers. The load balancers I already talked about. These are hardware devices that know how to take incoming IP request and then spray it out to a bunch of other IP addresses. Underneath those, we've got our racks. These are familiar with data centers, racks, basically cabinets. You slide in servers, and these servers we call nodes or blades or servers. And at the top of each one of these, sorry about that, at the top of each one of these, We've got top-of-rack routers. Actually, it's not so much that we've got them in the top of the racks anymore. A lot of times they're in the middle of the rack. We still call them top-of-rack routers. They're called top-of-rack routers because that's the way that all the servers talk out of that rack. Their communication to the outside world all goes through this router. At the bottom, you see we've got power distribution units. This is how we can control power to any server in that rack. Programmatically is by talking to that PDU. Say, turn off that server, turn on that server. Single points of failure. What component in this picture, if it failed, would cause an outage, would cause an application not to be able to talk to the outside world, and we'd fail our SLA? If you look, we're duplicating. We've got redundancy on the load balancers. We've got redundancy on the aggregators. We've got redundancy on the data center routers. The place where we don't have redundancy is the top-of-rack routers. It doesn't make economic sense at this point to put redundancy at the top-of-rack router. So that's our single point of failure in the data center. So how do we help manage failures of that single point of failure? What we do is, we've got in the application model, we've got this concept we call fault domains. And every application gets at least 2 fault domains. What that means is that when any of your tiers you've scaled out by n units, we'll spread you across these fault domains, these single points of failure. So for example, here I've got my 2-tier service, front ends and middle tiers. We'll spread you across fault domains, which in the current data center architecture is the top of racks. So you can see front end instances on 2 racks, the back end, the middle tier then across 3 racks. And if we have one rack fail, your service, yes, it's got reduced capacity. Your front end's down to 50% capacity. So hopefully this isn't during a peak load time for your application. At the worst case, the customers are going to have a degraded experience, but they're not going to have an experience where you are just not accessible at all, where they get a 404 that you're down, you're gone. So this is one way that we help ourselves, again, by building our own applications on this, as well as customers build high availability services. So the fault domain is really a way to model the unexpected case, a failure of the hardware. Let's talk about now how you update these applications, again, while maintaining availability of the application. Of course, the simple way to update an application is the kind of way that you do it on servers, which is you get the update, you run the setup program. Well, you actually get the update, you shut down the service, you run the setup program. Sometimes you have to reboot the machine. In Windows, unfortunately, you've got to do that a lot of times. You reboot the machine, and then your service comes back up, and now you're up and running again. But you had that outage during that update. We want to avoid that for the cloud, too, for a cloud application. This is where ScaleOut helps us there. And we also make it possible for you to tell us what's acceptable to you in terms of your outage for your application during that, or your reduced capacity during that update. There's 2 update types we support. One is the VIP swap update. This is where you deploy a new version of your service. The old one's still sitting there running. The load balancer is pointing at your old one. And then at some point you flip to the new one. And I'll show a picture of that more in a second. But the in-place update's what we do most typically for our own infrastructure services. And our customers we see really like the in-place update. This is where I don't have to create a brand new deployment of my app. I just update my existing one while it's running. And the way that we maintain availability there is by honoring update domains. So we will map the application across update domains, and by default you get 5 of them. So that means that most 20% of your application, any tier of your application will be down during an update. You give us an updated piece of code and say, update my front end with this new piece of code. What we do is shut down the front end, deploy the new code, and then start it up, and then wait for it to tell us, I'm ready now, I'm up, and I'm able to handle customer requests. Then the load balancer starts sending requests to it again. Once that first update domain's done, then we move to the second update domain, and so on. And the update Windows Azure SLA is based on you having at least 2 instances of your role of each of your tiers or your roles, because we want to help us give you that SLA of 99.95 in the face of hardware failures and in the face of updating applications like this. And here's the VIP swap. Here's the what we do is on the left side, there's the current version of the service. On the right side is the new version of the service. They both got internet-facing IP addresses pointing at them, so they're both accessible from the internet. And what we do is just take these IP addresses and swap them. So now the customers that were going to the production address now get routed to the new version of the service, and then you can shut down the old one. So that's how we do VIP swaps. Another example where a philosophy that we've used internally as we build our own infrastructure and try to make it reliable is that when we look at a system, for example, one of our own infrastructure components, kind of the equivalent of an app that's part of a larger app, we say to ourselves, what would happen if this thing completely failed? What's the impact on customer applications? And what's the impact, and as far as the impact, we want to do two things. One, we want to make it so that if any of our components fail, that it doesn't impact the customer's app. That the customer services that are continuously running there, your cloud applications, that they run and don't even see that we crashed or that we had a fault. In the worst case, we also say, well, you know what? Even if all else failed, let's try to contain the problem. And so what we do is define these containment units. We call them clusters today. They're about 1,000 machines in size. And this is this is the kind of unit that we manage the servers with a single piece of software called the Fabric Controller. It's like the kernel of the cloud operating system. It's sitting there managing about 1,000 machines. And when we update the Fabric Controller, we update the Fabric Controller for that 1,000 machine cluster. If the Fabric Controller failed, the applications continue to run on that. You get to some degraded service in terms of managing your application because you can't update your application while the Fabric Controller is offline. But your application's still sitting there talking to the outside world. So even there, though, we try to contain that kind of failure to just a small unit makes sense. So we got Fabric Controllers then across containing faults across those clusters. This is how we deploy new infrastructure software to the system on a cluster-by-cluster basis. So something goes wrong, horribly wrong, we say stop, let's roll that back, and then let's fix the problem, and then move on. And we might have affected some of the APIs that are available, some of the functionality that's available, but we have hopefully not affected the SLA for our customers. Talk just a little bit more about the Fabric Controller, because that's really the brains of the Windows Azure platform. And the Fabric Controller is, like I said, it's kind of a kernel of this cloud operating system. If you take a look at a desktop system, a kernel, it defines what an app is on the operating system. When you launch a process on Windows or Linux, it's the kernel that understands what a process is, how to load code into that process, how to activate that process. It understands when the process shuts down, what to do. The same thing is what the Fabric Controller does for cloud applications. When you deploy an application to Windows Azure, it's the Fabric Controller that knows this is what an app is, this is how I install it, and how I get it running. It also is responsible for managing the data center hardware, just like the kernel in a desktop operating system. How many people have taken an operating systems class, by the way? So a lot of you have, and so you know what I'm talking about. When I say the kernel is what's multiplexing the CPUs, it's multiplexing RAM, virtualizing the resource so that apps think they've got infinite RAM. Fabric Controller does the same thing, just at data center scale. The Fabric Controller itself, just to show you that we dog food the own model that we provide for customers, the Fabric Controller itself is modeled as a Fabric Controller application. It's a Windows Azure application itself. It gets deployed by a version of itself to a cluster. And it's got 5 fault domains because it needs to be super highly available. We can tolerate multiple rack failures and still have the Fabric Controller continue to operate without any interruption to anything, any APIs. So you can see there it's spread across. It's a stateful service, meaning that it's got data that if we lost it, it'd be a bad thing. So we're backing up that data all the time. But stateful means that whenever a change is made to the data center configuration, whether an application's being deployed or changing the hardware, that the Fabric Controller replicates the changes to the other replicas, the master Fabric Controller instance. Waits for that quorum to commit. It's a Paxos ring. And when that quorum is achieved, then it says, OK, I can change. And it's OK because if any of us fail, we can all reconstruct what's going on. And so the Fabric controller itself goes through this rolling update process that we've talked about, this in-place update. When we update the Fabric controller, actually we're updating it all the time. This is another aspect of the cloud I'll focus on a little bit more in a few minutes. But when you're working in the cloud, you're updating all the time. The key to updating well is that customers don't know you're updating. I think I can safely say that we can go to our customers today and say, do you know when the last time the Fabric controller was updated? And they'd have no idea, A, what I was talking about, and B, no, they wouldn't know when the last time we updated the infrastructure, even though we're doing it all the time. So I mentioned detecting a failure, and there's a few ways we detect failures. It's important for detection for the system to monitor itself and to try to detect errors in itself. It's also useful for something else to be looking at the system and try to detect errors, and we've got both concepts at play in different areas. I'm just going to talk about a couple examples here. We've got something called the Monitoring and Diagnostic Service. It's this service that any infrastructure component can spit data out to Windows Azure storage, durable store, and this logging system through logging APIs. Now this logging service then can go look at this data that's being generated and run analysis tasks on them. It can look for certain events that get spit out in the monitoring data that say, hey, I'm not healthy, or it can look for patterns that says this component's not operating correctly. And so that's part of the detection, is the components basically notifying the system themselves something's not healthy. And then we've got this outside view of the system called the Canary. By the way, that's the Windows Azure Operations Center right there, which is a room in the building, same building where Windows Azure is developed. There's roughly 7 people in that room. You can see a bunch of screens they're looking at to kind of a human eye on what's going on, the Operations Center. There's another one in another geographic location, mirror of this. In case something happened to this one, we still wouldn't lose our view of what's going on with the cloud. But this other outside view, one of the screens they've got is that view right there. It's called the Canary service. And the Canary service, it's a service which is a Windows Azure application. We deploy it everywhere. And that service is there to give us a view of how services are operating, kind of representative of customer services. This instances these virtual machines of the Canary service deployed to every single rack in every data center, and then they connected to every network device in every data center. So there's a Canary connected to every load balancer in the data centers. And what they do is they just sit there and they tweet at each other all day long, like probably or basically update their Facebook status all day long, and everybody's reading each other's Facebook status. And if somebody misses updating their status, they're like, oh, something's wrong with this my friend over here. He's been silent for a while, so I'm going to raise an alert, spit it out to MDS, and set what this is doing is monitoring that MDS data coming out of the Canary and saying, hey, there's a Canary there that says something's wrong. It's something wrong either with that Canary, it's like that Canary failed, something problem with the network. So it's a second view of end-to-end, how healthy is the system. And one of our lessons, too, we've learned, and actually anybody that runs operations at scale will tell you that they've learned, is get humans out of the way. The second you get a human involved with fixing a problem or configuring the system, you've got a high probability that something's going to go wrong. Almost every single major incident we've had in Windows Azure has been because somebody's going and configuring network hardware. And it's a lot of times they're like half asleep, it's the middle of the night, they're in the middle of their 17th network device configuration update, and they skip a step in the list. And the next thing you know, part of this rack is no longer able to talk to the outside world. Does anybody hear about the Amazon outage that happened a few months ago? And yeah, that was exactly the same situation. Human going and changing network configuration basically took part of their network off and caused a cascading set of failures that resulted in their outage. So that's our lesson. Where we can, we want to automate things. So more and more we're going to we've been putting automation into the system, and part of this whole thing, like if you look at the way that applications are updated, it's not humans going and running setup programs on each virtual machine. It's the Fabric controller going and automating this update. It's getting the humans out of the way. Another example of detection, which happens automatically in the system, again, no human intervention, is these load balancers are also programmed to probe the front ends. So you create this web front end. You say, I want 3 instances. Well, what if one of your front ends dies because it's on a server that fails? What if the software encounters a bug and it goes offline? You don't want customer requests to be sent to that dead instance. So what the load balancer is doing is continuously pinging those virtual machines. And if the virtual machine stops responding, the load balancer stops sending requests to that virtual machine. So as quickly as possible, customers are going to not be seeing that failure. Here's just another chart of some of the automated detection and recovery that we've got in the system. This is in place all over the system, and as we mature, we're putting more and more of this and getting smarter and smarter about how we detect, how we respond to these problems. Give you an example, obviously if the host operating system crashes, if the hypervisor crashes the whole server and all the virtual machines on that server. Well, first of all, you would say, well, isn't that a bug in the hypervisor that you should go fix? One of the reasons that we see, or the common reason we'll see a crash like this, isn't because of a bug in the software. It's because of a hardware problem. There's a memory problem, a disk problem. The disk just fails while the server's operating. Boom, that causes the software to crash. So what we'll do is at that point, we're continuously, everything is checking each other's health. The Fabric controller is pinging every server. Are you healthy? Are you healthy? If the server stops responding, we've got a timeout. Oh, this guy hasn't responded within a certain amount of time. Initiate recovery. At that point, we power off the thing. We'll power it on, try to get it going again. Maybe it was a transient error. If it's not, if it fails again, then we give up on it. We say that the server is sick, and we go and restart those virtual machines on a different server. And that's done all automatically. Another lesson that we've learned, and this is just any distributed system kind of lesson, is keep things loosely coupled and keep things asynchronous. Instead of sending a request from your front end to a particular worker and having a tight connection there, like I'm opening a socket to this guy, sending the request and I expect the answer to come back through the socket, what happens if that worker fails, then that connection dies. And now I've got to do the recovery logic. I've got to put in the detection for this failure in my app. I've got to initiate talking to another worker. So instead of sending a request to a specific instance, send them to all of them. Instead of waiting for an answer, go off and do something else and let the guy tell me when he's done. And that way, we're loosely coupled. If there's a failure, it's hidden from me. So here's the topology that we have implemented ourselves in most of our infrastructure, and we see customers doing in their applications, is using queues, these durable queues that we provide as a service. An API, you basically say stick a message in a queue, and then you can have your backends, your middle tiers, sit there and listen for messages to come off the queue. So if there's a work item for the middle tier, one of the front ends just sticks in the queue. The first backend that's available, that happens to pick up that message from the queue, will go and process it. Now let's say that guy's in the middle of processing it and fails. He's gone. The way that the queue works, it's a reliable queue designed for just this kind of problem. So that message reappears after some timeout. If the guy never came back and said, I'm done, the message pops back into life. And now another worker picks it up and processes it. And this is all asynchronous, so he'll stick the response back in another queue that the front end then will go and pick up. And now we've got a system where, with very little effort, we can tolerate failures of any of these components in the system. The load balancer is tolerating failures in the front end, and these queues tolerating failures in between these two instances because we followed the asynchronous loose coupling. Another lesson we learn, and this is just an obvious lesson, is, and I know that when you're in school, you're probably not doing much of this, is testing. Testing is a big pain in the rear, testing software. Most of the testing, I know, certainly when I'm writing my own code, is like I run it once and it looks like it worked and cool, let's move on. And so I might run it twice just to be sure. But when you're talking about building, especially the infrastructure, or you're building something like a Facebook, you're building anything where a failure can be a problem for you, your business, or your customers, you need to test, test, test. And so we've got this philosophy of testing deeply, deeply ingrained in a sense that's way deeper than what Microsoft's traditionally seen as testing's role in the software development cycle. If you look at Microsoft, like most software companies, has been in this world for a long time of delivering what we call box products. Every 2 years, we spit out another box. And the way that we produce that box of bits is that we ship one version of the box, and then we say, okay, let's plan the next version. What features do customers want? Where do we need to finish improving things? What features should we add to make the thing cooler? We plan it, then we start coding it. The developers finish coding it. They hand it over to the test guys. The test guys go and hammer it, make sure that it looks okay, file bugs. The developers fix the bugs. Once those bugs are fixed, the bug count never gets to 0. It's just a matter of which bugs are tolerable and which aren't. That's one of the interesting things you'll learn out in the real world, is that every piece of software ships with known bugs. And it's a matter of managing the risk of those bugs. If you shipped with 0 bugs, you'd never ship anything at all, and nobody would even give a crap that you had no bugs in your software. But hopefully you're shipping software with bugs nobody sees, nobody is impacted by, or a very tiny percentage, so the risk is very small. In any case, that's the traditional model. And then testers test it, say it's cool, you put a box around the bits, and then you ship it, and then the process starts over. When it comes to cloud, we're always shipping, like I said. And you can't just ship and forget it. And you can't just ship and hope that the cloud tests it and the customers run into it. And you can't do this box product thing. You're always shipping small things, and that means testing has to just be there through the whole process. So developers, the developer and test boundary starts to disappear. In fact, we've seen this in the kind of behavior that the model drives in the Fabric Controller team. We've actually codified it and made it formal. The developers are going to do their own functional testing. They're going to work with the test team, which does more integrated more integrated testing across the whole component, of coming up with the test plan together, instead of the testers just coming up with their own test plans based on the specs. The developers actually come up with them, and the developers are writing their own functional tests. So the lessons that we learned here: test on the dev's box, test with other components. We call this integration testing. And then test in a production-like environment before you go to production. We call this stage. And another one is release early, release often, release focused. And what I mean by that is you want to fix your system, you want to improve it, you want to add new features. And you need to do this at cloud speed, so you're always shipping the new stuff. Release focused means when you have these releases, don't throw a ton of major stuff into it. That's a recipe for disaster. You put in 3 big features in a release, and then that release starts to fail. You've got now not just how to figure out what's going on, but which of these features is causing the problem. It's much easier if you do a major release of one big feature. When there's a failure, you know who's responsible, most likely, and so you can go address it. And by releasing often, you actually avoid the syndrome that leads to a whole bunch of big features in one release. Because developers, when they're developing, they want to have their stuff released. And if you're releasing once every 6 months or once every 2 years, you better have your crap done to get that release, or else you're on the next train, which is 2 years later. And who wants to do that? I mean, we saw this behavior when I was in Windows, of developers going, crap, I better get this done by this, the end of the coding milestone. If I don't get it, I'm not going to be in the box. And I'm going to be then out of luck for another 3 years, and my last 2 years of development wasted. That's the way they view it, right? Because if you don't get it out in the box, 2 years is a lifetime. I might be working for another company at that point. So with releasing often, developers don't have that angst. It's like, okay, if I miss this 6-week interval, I just pick up on the next 6 weeks. 6 weeks, not that big of a deal. This is actually a snapshot of our release pipeline. You can see that as we move through these things, we spend a few days to a week in each of these stages. This is actually taken right from an email. We've got a release lab. All these different components are moving through it at the same time. Everybody's loosely coupled. This is kind of like designing it for the modern internet age of everybody's just constantly shipping. I mean, people talk about, oh, I want to go to a startup because startups move fast, or they release fast. I don't want to go to a big software company because they're slow. Well, that's the old big software company. This is the new big software company right here. And then finally, I talked about dev and test merging. Well, dev and operation, when it comes to cloud, you've got this new component, which is operations. Somebody's running the software every day. With the box product, you give it to somebody else, and they do their own ops, whatever. It's their problem at that point. You've handed it off. When you're running it yourself, it's your problem. If there's crap that breaks, it's your problem. You need to fix it. And that means that the developers need to be, they're on the line. Their butt's on the line. If there's crap broken with their stuff, get them on the phone. Have them figure out what's wrong, how to fix it, and what bugs should be fixed for the next release. This is actually, again, every week we send out an email that says this is the on-call schedule for the week. And this is actually copied right from an email coming out of one component, the Fabric Controller team, Fabric Core. You can see we've got 4 different devs for each of these days on call. It's a 24-hour shift. You can see they can be called by those guys in that operations room. If they can't figure out what's going on, these guys get called up. And they suspect it's in this component. These guys get called up. And they've got if it's 3 o'clock in the morning, it's your stuff to help figure out what's going on. That's also encouragement to have good testing, too, right? You don't want to be woken up at 3 in the morning because something's wrong with your code. And actually, it might not even be your code. It might be the guy in the office next door, which would really piss you off. So you want to make sure he's testing his stuff, too. So that's kind of the virtuous cycle we've got going with cloud DevOps and test. And that brings me to the end of the presentation. What I wanted to do was just convey to you a little bit of what basically, this cloud buzzword that you hear everybody talking about. What is the cloud, the different flavors of cloud, and then when it comes to building for the cloud, whether it's somebody like us building the cloud infrastructure or somebody that could be one of you building a cloud service for your mobile application or your new cool social networking startup, some of the lessons that we've learned as we do it. Detect failure fast, fail fast, design redundancy, contain failures, async loosely coupled architectures, test heavily, release frequently, and DevOps is the new way that devs should be viewing the world. And finally, the world is moving to cloud. Everything that I've talked about, the benefits of the cloud, the economics of the cloud, the outsourcing, all the features that I talked about the cloud, you can see that here's Gartner and Forrester, 2 of the trusted IT analyst organizations that are looking at industry trends. These guys are saying what I believe is absolutely true, is that if you go start a software company today, how many people think they're going to start a software company after they graduate? Anybody? Just a few? That's it? You're all going to come to work at Microsoft? No. If you go start a software company, do you think you'd really go buy a server? Probably not. Chances are pretty close to 0 you'll buy your own server. You will go and deploy your application to App Engine, us, or Amazon. You'll use one of our servers and our infrastructure to run your stuff. Why buy your own server? You can see that playing out here where Gartner says that 20% of businesses next year, they're saying, I think that's a little aggressive, are going to own no IT assets. I certainly think that long term what you're going to see is first, small businesses, they're going to get rid of their servers. They're going to go to software as a service. Then you're going to see mid-sized companies say, why do we need servers? The last ones you're going to see are the enterprises. The enterprises are going to actually go in a weird hybrid mode where they're going to say, first, I'll put my crap I don't really care about up in the cloud. Use somebody else's servers. The crap I care about, I'll keep myself. And then eventually they'll say, well, you know what? All these other people that would started out with no crap themselves, they're operating a lot more efficiently. I better get rid of my crap, and they'll throw all their stuff up into the cloud to be able to compete. And so I think that epoch that we see is really going to dramatically play out just because of the force of the economics of this over the next 10 years. So with that, I want to just point out that I do get social networking. So there I am on Facebook and Twitter. Feel free to like me and to tweet me, and I'll tweet you back. So with that, I'll open up the floor to questions. Yes, in the back, very back there.
What are your thoughts
So what I think of open source and OpenStack, I think for some scenarios, I mean, I can't equivocally say one way or another whether it's good or bad. It depends on what you expect to get out of it and how it meets your needs. I think that, just like Linux has shown that there's thriving need and places where open source software makes sense, it's going to make sense for a lot of people. I think there's other cases where you're going to actually not want to have to deal with it yourself. And I think that one of the things that we see at Microsoft is, even for the open source stuff, it's not like they want, they're not looking at it as open source so much. They're looking at it as, how much does it cost me? And what can I do with it? Not is it, hey, I'm just cool and into open source. Because when you're running your business, the last thing you really want to get into is a philosophic thing about what kind of software development philosophy the software that I'm using has got. Really, I care about whether my business can survive on this. And so when you look at enterprises, even their adoption of open source, it's not like they're building Linux in their own labs and then deploying Linux. They're going out and getting it from Red Hat, which actually in certain types of Linux deployments can cost more even out of the box than Windows does. But customers like it because of the software that can run on top of that and because they're getting the support from Red Hat, not because it's necessarily because it's open source. Yeah?
So when is Microsoft planning to deploy all their internal services on Windows Azure?
So that's a really good question. It's about when Microsoft expects to deploy all its own services onto Windows Azure. Already you're seeing, so Windows Azure, to give you an idea of how old it is, we first started charging for it in February of last year. So it's not even 2 years old yet. It's very young. And Microsoft, of course, has been building cloud applications for a long time on its own infrastructures, on common shared infrastructures, on some internal group at Microsoft builds their own app and they'll build their own stuff. But now that there's Azure and now we've actually proven it and people understand what it is, what we're seeing is an organic adoption of Azure within the company. So there's lots of subsites off Microsoft.com that have already moved to Azure. There's Bing Games. If you go play Bing Games, if you do anything with Bing, that's a good thing to do with it, is go play games. Bing Games all run on Windows Azure. There's Xbox properties that run on Windows Azure. And Steve Ballmer, our CEO of Microsoft, has actually said unequivocally to Microsoft, we're all in, the cloud is the future, and the cloud platform for Microsoft is Azure. So that means that anybody creating a new application with Windows Azure will be on Windows Azure. There's properties like Office 365, you might have heard of, one of the software-as-a-service examples. This is essentially email and SharePoint and other IT applications hosted in Microsoft's cloud. That was built before Windows Azure was ready, so it's built on a different infrastructure, but what we've got going on now is working closely with them to start to migrate them onto Windows Azure. It makes economic sense for us to have one cloud platform this stuff runs on. Question back here. So the question is, when is Windows itself going to be storing application settings? Actually, at the Build conference, which was Microsoft's professional developers conference a few weeks ago, where they talked about Windows 8 and config syncing for the new style of apps they call the immersive apps up through the cloud. Yeah?
For industries like banking, health insurance, and health industries, what do you deal with privacy issues with cloud?
It's a good question. So the industries that are very concerned with privacy and data security, what's going on with the cloud with them? Those are some of the companies that are going to be last and most resistant and skeptical of public cloud platforms like Windows Azure. We're addressing this in two different ways. One way is that we're committed to making what's called the Windows Azure Platform Appliance, WAPA, which is kind of like the Whopper from War Games. And actually, that's what I think of as this machine. It's big and it's doing lots of really cool stuff and lights are blinking everywhere. That's Windows Azure Platform Appliance. What this will let people do is put Windows Azure in their own data center. A lot of the companies that I think are going to be the ones resistant to moving to public cloud, in fact, some of them might be forever operating in this manner, is with a private cloud with Windows Azure Platform Appliance. So hopefully we'll be addressing that. We've got 4 deployments of the appliance today, one at Fujitsu, one at eBay, one at Dell, and one at HP. And that is serving as our first step to learning what it means to let other people run Windows Azure in their own data centers, and we'll be expanding that program so that it might address them. The second one is a lot of the skepticism about public cloud is like, are you secure? What are you doing about data security? And it's not good enough for us to say, hey, we're doing a damn good job, so trust us. For some companies, that's good enough. You know, they trust Microsoft. But for companies that are saying that some of them are regulated, and they are regulated with requirements that say you cannot deploy your application or data into some hardware or software environment that's doesn't have these certifications. It could be ISO 27001 or FISMA, which is a government certification. So what we're doing is filling those in. You'll see us get more of these industry standard certifications that basically say, somebody can go look at it and say, Windows Azure does this, this, and this, and this, and this, and has satisfied this certification, so that means we believe that it's okay to store our data in it. Yeah, right back.
So say you go to Windows Azure Platform-as-a-Service and start going really well, you start having a good volume, stuff, and you get somebody to invest a whole bunch of money in you. How does Windows Azure compare? And I know you had some slides about that, but if you're in a platform-as-a-service realm, how much can you still throw money at the problem? I mean, I know that's kind of a concern sometimes if you're on a more restricted system like App Engine. You lose the ability to say, I just want faster servers. I don't have time to buy, I can't find new developers. Where's Windows Azure?
So I'm not sure I understand the question. It sounds like you're talking about scaling out.
Like if you go to platform-as-a-service route, how many times do you find people that are stuck in situations where they say, I just need more machines than Windows Azure's algorithms. I'm giving them to
Yeah. So unfortunately, we haven't run into that situation yet. I think it's a good problem to have, is somebody to come and say, we need more servers than you've got. But that's bad from our perspective. It's good from our customers' perspective. We've got some customers, the risk metrics that I talked about on one of those first slides. They basically have these batch jobs that are thousands of computers and that run for 12 hours, 24 hours at a time, analyzing their business data on us. And all we need to know is, when do you need it, and how long are you going to need it, so we can plan around it. But we make every effort. We've not been able, there's not been a case where they've come to us and said, we need X thousands of servers to run this, and we say, sorry, we don't have that. And we're aggressively building out our data centers. I talked about the growth of our storage, going from 70 petabytes to 200. I talked also that we've got several tens of thousands of servers. We'd be doubling that in the next year to make sure we don't run into that problem. So we're the ones that have to deal with the kind of server allocation problem so that you don't. Yeah, right here. Yeah. So a merging of public clouds? Will you ever see that? No. Well, so one of the things that we see people asking for is they don't want, some of the customers, when they're looking at public clouds, they don't want vendor lock-in. They say, well, if I start to adopt your platform as a service, then I'm stuck with you. And then you can screw me on price. And I have no choice. It's going to cost me a lot of money to move off you. And so we see this demand or this request from people that are hesitant. They really haven't even seriously taken a look at the cloud, but the first thing is vendor lock-in. What do I do about that? That they say, hey, why don't you just standardize your storage APIs? Why don't you, Amazon, Microsoft, have the same storage APIs so I can just move between one and another of you. I think you might see standardization at the layers where it's commoditization. But it certainly doesn't make sense for us or for our customers for us to be like, talking to Amazon and saying, hey, let's do the exact same thing because we want to look like the exact same service to people. We want to actually give you great service. We want to make it easier to run your business and save you money and to create these kinds of applications. And so it's in our best interest, it's in your best interest for us to be doing that. Now, whether you decide it's economically worth your while to opt into those features and potentially make it harder to come off the system if you want to move somewhere else, that's a business call, but we're not going to stop by, not doing things that would be helpful for people. Yeah, and very back.
Last year, maybe early this year, Amazon went down for a little while. The cloud in general is very young. Do you know any
Statistics on what we can expect about the cloud going down. Yeah. We will not. So Windows Azure will not go down. That's my prediction. Yeah. Yes, you can quote me on that. Yeah. Yeah. Very back. So challenges around debugging kind of distributed applications like we're debugging is the question, and it's a challenging problem. I think part of it is that to make it easier is we have simulators. We've got a simulator ourselves for running our own infrastructure on our desktops. We've got small-scale implementations of our systems that we can run in our own offices with a few blades. And for customers writing cloud applications, we've got something we call the cloud emulator, compute emulator, which you can run on your desktop and simulate your application running. So literally within Visual Studio, you can set breakpoints on the different tiers. And to you, it seems seamless, right, as far as the debugging experience. So that's one of the ways, a couple of the ways that we're trying to make it easier to debug. We also have diagnostic services that you can call out to so you can emit diagnostic information about what's going on inside of your various instances and then look at that to see what's happened. Yes, right over here.
Do you think the cloud will be capable of running Skynet?
Capable of running Skynet. I'm absolutely convinced of it. I mean, if you saw the Watson thing, combine Watson with Windows Azure and you've got Skynet. Yeah.
Do you think that we'll see the cloud increasingly used to back up the computational ability of mobile devices or a la Amazon Silk browser?
Do I see it backing up the computational? So what do you mean by backing up?
I mean, like, do you think that mobile devices will make use of cloud computing in the future to sort of back up their own process?
Yeah, actually, there's a lot of that already going on today. There's a lot of, today with phone apps, that voice recognitions, music recognition apps, they're using cloud back-end services. So anything where anything is massively data intensive or computationally intensive, already you're seeing these architectures where the mobile app is just the interface to the cloud doing most of the work, but from the end user's perspective, you can't tell that's going on. Yeah?
How do you keep these applications from either abusing or glitching cloud out?
How do we stop them from abusing or glitching the cloud? Very carefully. So the question is, how do we stop them from abusing the cloud? I think one of the ways that you can imagine abusing the cloud is people signing up, deploying a cloud application, which is really a botnet, and serving up stuff off it, interesting pictures off it, or attacking somebody. This is a problem that we all face in the public cloud space, and there's some tricky issues there that I don't think have been fully ironed out about when you detect somebody performing some activity that you think is undesirable, how to go about responding to it. There's all sorts of legal implications to freedom of speech and whatever, and being able to look closely at what they're doing without warrants and things like that. So this is an area that I think is not fully explored yet when it comes to that. Yeah, John.
Speaking of freedom of speech, what do you do about multiple jurisdictions of laws? For example, if somebody from Cuba wanted to use the cloud.
Yeah. So what do we do about multiple jurisdictions? I'm not a lawyer, so I can't really speak authoritatively on it, but I think and just so that I don't look like I'm just brushing off the question altogether, I think this is another area that's not explored yet either. This is the kind of scenario where, and to take it one step further, there's a company in Europe that believes that there's been a breach in their cloud provider in the US. And they say, we need access to your cloud infrastructure to do forensics to see what was going on there. And you've got now European laws and US laws and other customers' data sitting there, and that we haven't seen any of that play out yet either, which I think is inevitable that eventually that will too. Like, how does the process to handle that go? Yeah, so I don't have a good answer for you. Again, I'm not a lawyer, so. Yes?
You being a cybersecurity expert, how do you see the cloud in helping reduce those risks? Because, like you said, the operating system can be patched
Actually, I see it. So the question is, do I see the cloud reducing the risk of cybersecurity issues? I think that it depends on the way you look at it. If you look at it from one perspective, if my own data, like I'm a business and I've got my data and my compute running here on this server, I've got some kind of security through obscurity and kind of being a small fish kind of target. So chance of me getting hacked, somebody targeting me, might be relatively low. On the other hand, I probably am not, given my limited resources, not willing to spend them in putting in the best security practices in protecting the physical security of the systems and making sure that the best security software is there and the security personnel are there to model the architecture of the system and the network to make and model what happens if there's breaches. If you look at the cloud, though, that's where it's in our best interest to put lots of money at the security problem. Security is one of the, there's two things that I think are kind of the bastions of trust for the cloud. One is, besides not screwing people with price, but one is disasters, being able to tolerate disasters well, and the other one is security, making sure that the cloud is secure. Failure in either one of those categories could potentially be the end of the business, or certainly a big impact. So the Amazon thing, if that had been significantly bigger, that could have had a bigger impact on all of us. Fortunately, people see it as a growing pain kind of thing, and it didn't affect people too badly, so people have gotten over it. So it's in our best interest to make sure that we're hiring the best security experts. We've got systems that are very homogeneous, that are simple as possible so we can understand them from a security perspective. We put in the best security intrusion detection and antivirus and also all the best practices. It makes it harder for somebody to breach us. On the other hand, the cloud is a very juicy target. If somebody figures out how to breach the cloud, they get access not just to Microsoft, they get access to everybody else that's hosted on the cloud. So I don't think it's a black and white game with that.
I mean, I know you have the book.
Oh, yeah.
Question for that, if you could do that, and then.
So I've got the book, Zero Day. It's a cyber thriller. It's about terrorists using malware, actually, to bring down, to cause havoc, and a couple of people coming to the rescue. It's just to give you an idea, it's actually got some pretty good reviews. Let me, if I can figure out how to exit end show. See if I can launch. Who likes Chrome? Who likes Firefox? Let's take a vote, Chrome. All right. Do I have a key? So here's the book's website. So you can see it's actually got some pretty good reviews. I actually have a video too that I'll show you.
Terror is only a keystroke away. Anyone can be the target. The countdown has begun. 0 Day. A new techno thriller by Mark Russinovich.
Yeah, if you know somebody in Hollywood, I'd be glad. Please set me up. All right, so I'm going to give this away. I'm going to ask a question. The first person that answers the question gets the book, and I'll send it to you. Who was the original architect of Windows NT? Dave Cutler. Yeah. Okay. There we go. Yeah. What's your name? Danny? All right. Well, actually, I'll sign this book away, but I think we're probably out of time. So thanks, everybody, for having me. I hope you found the talk interesting, and you're proud.
So thank you, Mark. All right, guys, at this point, dinner is ready. If you guys want to go upstairs and line up the